Awesome. And I don't know how many more of these seminars we're going to have, but if you're interested in giving one, I'm more than happy to facilitate. I feel like I learn a lot from everyone, and we have really great discussions. So please do get in touch if you're interested. With that, I'm just going to hand it over to Menno, who's going to be sharing some awesome results on, I don't know what all you're going to be including, cable burial and port operations and all sorts of fun things. So take it away.
Thank you for the introduction. And indeed, I also learned a lot from the RCN group. That's how Hannah and I also got in touch. So I would say anyone who's interested in a follow-up, please feel free to reach out to me or to anyone else, I would say, and let's hope we can give this group some more exposure.
As you're getting set up, I'll just say, if you have a question, feel free to put it in the chat and we can read it out at the end. But we will save all questions until the end when we'll have time for discussion. So thanks all for joining.
So today I would like to talk with you about monitoring the nautical depth with optical fibers, which I understand is a little bit of a niche in DAS. However, there is a lot of merit in it because we can look at, for instance, cable burial depth. We can look at, for instance, flows and all kinds of other features that could or may also be applied in oceanography and in other fields. So what I want to do is, by recording vessel movements or other passive noises, and then create a nautical depth chart throughout the port of Rotterdam or in other ports. Now, why do we want to do that? Current methods are often lacking repeatability, are invasive, and are point measurements, whilst these river conditions are very dynamic. So what you can see is a vessel moving with a echo sounder, which is a known nautical depth surveying method. It sends a pulse, it records the pulse, and it receives a two-way travel time. However, this method is often not very accurate due to mixing of saline and fresh water and due to temperature variations, which is why we don't know our P-wave velocity accurately. So then they use calibration tools, as you can see in the middle, and these are point measurements. And you can imagine if we have a very large port, such as the port of Rotterdam, spanning over more than 40 kilometers, and you have to start poking every channel, it's very time consuming. Furthermore, after a storm, we may or may not have meters of sediments deposited, and then you have to resurvey again throughout the entire port. And this may take up to 2 months. Now then, about distributed acoustic sensing, I will leave it short because I assume most people are already familiar with it. We send a laser down an optical fiber and we retrieve a phase change per radiance. And this gives us some indications of where the reverberation is, where the disturbance in the fiber is, and we retrieve both phase information and location, and hence that we can use it as a quasi geophone or quasi hydrophone. And what is interesting about this is that we can probe very long fibers nowadays, and we can measure all types of signals, such as vessels, but even whales. Now, what we then want to do is create a network that gives the nautical depths to ships and vessels, captains, and continuously give a sort of feedback of how deep it is. So we already do that with the tides, because we can measure the tides and predict them quite accurately. And we also want to do that now with sediments to complete the whole nautical depth chart. And this information will be then also transferred via optical fibers, go to a radio tower where we can transmit it, and then people can receive it on their phone, for example. Now, the first thing we did with optical fibers was to conduct a lab experiment where we coiled a fiber onto a PVC pipe, a very simplistic setup. And this setup only costed a few tens of euros. Then we put a source on top and start to receive our signals. And what you can see here is the orange lump on top of the column This is a dual echo sounder. It's been taken from a surveying vessel. And once we use it as a source, the acoustic energy is trapped in the water column, as we would expect. You can observe it on the yellow part here. And this was to give a first indication, okay, how accurate can we capture such an interface? And we could manage it very accurately up to a few millimeters if we have such a densely spaced coiled VSP setup. Then the next thing we wanted to do was to create a similar setup in the port of Rotterdam. Here we also created a VSP like we did in the lab, and then we started to record vessel noise. Now, we did multiple experiments. We had built two setups, one with horizontal fibers between two poles, and one only a coiled fiber. Now, we expected everything to be flat and straight. However, it wasn't, that the dive inspection revealed. But this also gave us new opportunities to image such a mud anomaly. Now, the other thing we did then was the VSP setup. We were purely focused on the coils or no VSP setup. And here we lowered the mantle, as you can see here, and allowed it to be completely submerged into sediments to see what we can also say about the sediments. What is, for instance, the yield strength? How much resistance would this material expose onto the vessel if the vessel would sail through it? So then the first thing we wanted to know is whether we actually can measure shipping noise. So we started to record when a vessel passed, and immediately we could pick when the vessel had passed. Here highlighted in red, you can see the ship moving by, and this allowed us to give a feeling about the frequencies that the ship has emitted, and also how strong our signal to noise ratio is. Then we created a PSD when we had our mantle partially submerged in water and partially submerged in mud. And what we noticed is that the acoustic energy again is mainly prominent in water and not so much in mud. This might also be intuitive because the mud that we have, that we talk about, it is very liquid-like. And you can even imagine it to be something like chocolate milk. And there are certain drag forces on that cause a lot of attenuation for P waves. But then we wanted to say something about the mud. The reason why we want to do that is because current surveying methods, they are purely based on density. And like dairy products, the yield strength or the shear stresses relation to density is nonlinear. This means that in our current criterion, butter would be more favorable to sail through than skim yogurt, whereas we know we would much rather have skim yogurt to sail through than butter. So what we did, we created a bentonite suspension. We mixed it with a very powerful drill. This bentonite is very difficult to mix, so it took a lot of work. And then we filled our column with bentonite and partially with sand, but just to fill up the column more, such that we didn't have to have too much bentonite suspension. And we left it over a day. And then we started to notice that our signal penetration became much better after the bentonite settling for one day. Now, bentonite has a very particular behavior. It doesn't sedimentate, it only increases in shear strength. And you can imagine this stuff to really become like a pudding. But because the density doesn't change, it allows us to purely relate the change in acoustic signals to a change in shear stresses. Now, initially, before we let the bentonite settle for 24 hours, our yield point of the fluidic yield point of the bentonite was 17 pascals. And then after a day, it was 48 pascals. And this is a very big change in yield stresses. Now, and that was for us a very good thing to realize that our signal penetration becomes much better once the material increases in yield strength. So then when we apply a similar principle in the Port of Rotterdam, when we lower the mantle down to a depth of 6.9 meters, we start to notice that our lower frequencies increase, whereas our high frequencies decrease. So we see a reverse trend, which is not exactly what we expected from the laboratory setup. We would expect the higher frequencies to be more prominent or to increase with an increasing depth. But we see only the lower frequencies to increase. Now, this could be related to a coupling effect. As you can see over here, I've highlighted a small anomaly with a red arrow. And this is where we taped the fiber to the pole again. Here, during insulation, the fiber broke. And due to the tape, the coupling was increased. And because the coupling increased, we believe it became more susceptible to lower frequency waves. So what we expect is that the fiber is able to move with the lower frequency waves, which may be flow, which may be something else. We're not sure of what causes these lower frequencies. But when it's taped down to the pole, it has to elongate and extend. Now, and we can see these lower frequencies increasing in amplitude with increasing depths. And when we lower it, it becomes more and more prominent. Whereas if we look at the higher frequencies here, they become far less prominent. And this gave us an indication, if we have a VSP setup, that we are able to capture the water-mud interface and also get an indication about the yield stress of the sediments that we have. Because ultimately, we'd like to be able to capture these rheological properties of the sediments to know if we can sail through these chocolate milk layers. Now, unfortunately, the Port of Rotterdam would not like me to install poles all over the place, which is why we also welded a few rings on it, as you can see over here. And then we looped the fiber, as you can see here, through these rings to create also a horizontal setup. And the nice thing about this setup is that we have different coupling effects while having a horizontal fiber, and we have different heights. The increments here are 30 centimeter, and then 60 and 60 centimeters. So we can capture passing vessels, we can capture flows at different burial depths. Now, this schematic setup we created after a dive inspection, and the dive inspection revealed that we have about 2 meters here from the pole to the mud anomaly, and that here it was about 32 meters to the mud anomaly, and that we had 2 fibers here laying on top of this anomaly, and 1 was buried in the fiber. And our top 2 lines, they were completely suspended in water. Now here you can see a picture when we were installing it. Here we see the mantles being slidden over the poles, and you can see the fibers hanging between them. So we lower the mantles, then we tighten the fibers such that we have minimum slack. Of course, because this is done manually, the slack does differ per line, which was also observed by the divers when they start to pull the fiber just a little. Then we identified 3 different sources to monitor the water-sediment interface. One is seafloor compliance, one is propeller cavitation or vessel movement, and one is vortex-induced vibrations. Now, again, the first thing we started to ask ourselves, can we measure vessel movements with straight horizontal fibers, or can we only do it when coiled? Here I highlighted 2 particular vessels that came by. One you can see has a very nice hyperbola, and one seems to deflect. The hyperbola is not very well behaved. Now, what we first saw was a very nice hyperbola, and we could see that if the vessel moves very fast, the hyperbola becomes very sharp, and if it's very slow, then it becomes more stump. Not very exciting, but it was for us good to know. And then we had this more interesting feature, I would say, when we saw at first the hyperbola appear to be well behaved, and then it seemed to become more stump. And this asymmetrical pattern was related to the course of the vessel. One vessel passed us straight by, that was the first one with the nice hyperbola I showed, whereas the second one, it turned and started to dock in the Gulhaven, which is behind our setup. And this means that the trajectory of the vessel with respect to us, the observer, our fiber, has changed, giving us these asymmetrical patterns. Now, that's good for us to know that we have these asymmetrical patterns, because only something, nothing natural could cause these asymmetrical patterns. So we know, okay, it must be related to the vessels and their trajectory. Now, then when we create a power spectral density of all channels, and we look at where do we receive most acoustic energy, we start to notice a few things, very interesting features. We have here a sort of more darker spot, and we have here a more darker spot, and we have here a more darker spot. And that is related to the muting of the sediments to the propeller cavitation. So what we saw on the first line, that is here partially buried, at first is exposed in water, it's suspended in water, and we get very strong signals. Then when it moves into the sediments, we start to lose our signal. And this is a very interesting feature, because it means that we can already say something about the location of the sediments only by creating a power spectral density, which is not very computational intensive calculation. And what is interesting is, as I showed before, the time length that we had was just a few minutes. Now we go here from the lowest line right here, all the way up to the highest line, all the way here that is completely suspended in water. And what we can observe is this sort of hyperbola feature, for example, here. And that is because our fiber goes back and forth between the lines. So we expect a sort of mirrored behavior. And this is also what we observe, for instance, here. Now you can see very interesting constructive and destructive interference patterns. We believe this is related to the depth and the vessel location, because these patterns didn't change once the vessel location with respect to our setup changes. Now on to the next step, our next passive source that we used for nautical depth imaging. This was the vortex-induced vibrations. And this is related to the currents, to the tides. Now, why do I believe that is related to currents or tides? That is because if we look at it per channel, so not when we don't look at all channels, but one channel at a time, we start to observe a fluctuation. And notice that the time scale here is for very large length. So this is about 5.5 days. And we start to see a frequency oscillation. And this frequency oscillations period is about 12.5 hours. And this is the double tidal period in the Port of Rotterdam. So what this reminds, or may remind us of, is when you have a bottle and you fill it up with water and you start to blow in it, you also hear this changing frequency. So in a way, it becomes a sort of an indication of what the water column height is when it's exposed to some current or some flow. Now we had two poles at different depths, and you can see here the frequency is about 1.8 to 2 hertz. And for the that is for the deeper pole, and for the shallower pole, we noticed the fluctuation, the bandwidth of these oscillations is much larger, and the frequencies are much higher. Also, if you zoom into these frequency oscillations, we were also able to pick the water level up to maybe 10 centimeters accurately. Now, what's also interesting is that the flow velocity does not seem to align with these frequencies oscillations, but only the water level. And what I mean with that is that if we look at the picture here and we observe or compare the green line and the orange line to these oscillations, we see that the orange line matches these oscillations quite well, whereas the green line does not really seem to align with these frequencies oscillations. Now, the green line is the tidal flow. So this is the calculated flow due to the tidal change, which changes or has a period of half the tidal height. And initially, we thought that these vortex-induced vibrations would be related to the tidal flow because we expected that the flow would ultimately determine the frequency of these oscillations. But it turned out that it's not the flow, but it's the tidal height. Now, this can be related to the exposure of our poles to the water column, so that as it alternates, the frequency or that it resonates on because of the flow starts to change. But it's something that might be interesting to think about, that the relationship between the vortex-induced vibrations and the flow might be more complex than at least we initially thought. Then furthermore, what we also start to notice is, because our setup is aligned with a channel, if we have a seaward location, it is mainly the deeper pole that we measure. And if we have a landward flow, then we have mainly the shallower pole that we measure. And that is because our seaward tidal flow moves this way, as indicated by the red arrow, and our landward tidal flow moves this way, as indicated with the blue arrow. And you can imagine, once one of these poles starts to resonate and the vortexes, they move this way, then we mainly capture, of course, this one. Whereas if this one moves that way, we won't really measure it. So that we also see in our power spectral density, if we take, for instance, a channel in the middle, then once there is a tidal rise, we mainly measure the lower frequencies from the deeper, originating from the deeper pole. And if there's a tidal fall, we mainly measure the higher frequencies originating from the shallower pole. Now, if we compare channel E and F, the ones over here, we also notice that once our channel is buried in mud, and we talk about a burial depth of just a few centimeters, 5 to 10, it differs per location, we also see that our signal is almost completely lost. We can still see some small features, but it is muted a lot. This is also intuitive because the movement happens mainly in water, of course, and hence that if we bury our fiber, we will not really be able to detect this movement. And that can also be an interesting method to measure, for instance, cable burial or see if your cable is exposed in water. And then finally, our referred source. This is related to seafloor compliance, what we believe. We are 15 kilometers away from the sea, yet still we started to measure these ultra low frequencies. Initially, we thought this might be a temperature effect, but if we observe a signal with 0.02 hertz, which is 50 seconds, we do not expect any temperature change to occur. Furthermore, if our fiber is pressed against the mud, we would still expect a similar temperature change as the fiber that would be suspended in water, because ultimately both are in water. However, that's not what we observed. And what we did observe were very sharp boundaries, but this might be also related that we took a period of 5.5 days to create this PSD. One of the reasons why we could do that with still a lot of channels is because we are able to downsample a lot when using these ultra low frequencies. So what might be at play, and we're still not entirely sure about this, is that we have some offshore infragravity waves that press on the sediments that make our poles go up and down or something like that. And what is interesting here, though, is that the 2 meters of exposed fiber that we have over here, we were still able to image with these very low frequencies. Now, then when we look at this method, when we look at DAS, and we compare it with a surveying vessel, it becomes obvious that DAS has a lot of potential. So what we were able to image was a section of 2 meters over here, giving us a minimal horizontal resolution of 2 meters, even with a gauge length of 3 meters and a channel spacing of 1 meter. And we had a vertical resolution of less than 6 millimeters. And that's because we used a direct burial cable that is 6 millimeters in diameter. And once it's pressed against the mud, we immediately start to lose all of our passive sources. Now, with the newer generations of interrogators, we can use lines of over 100 kilometers. And if we then compare the cost of a fiber, which if you look on very cheap websites, then you see, okay, maybe 8 cents per meter. And we know we can operate it, a single person can operate it. Plus we have temporal resolution of something in the order of 10 minutes, because we still want to have some data that we calculate, that we integrate over for a PSD. It becomes very interesting if you compare it to a surveying vessel or to any electric transducer. Now, these surveying vessels, they may or may not have the same resolution. That depends a bit on how much tidal mixing there is, how much freshwater, seawater, and how many temperature anomalies there are, and also the depth. But the surveying vessels, they are usually manned by a crew of 5, 6, 7 people, and they take many days to survey the whole course or the whole area, which is costly. And it gets obstructed by traffic, and it is obstructing other traffic. Now, fibers, on the other hand, we can continuously monitor. The fibers themselves are very durable, and they're not that expensive. Of course, the interrogator is expensive, but the fibers themselves, not so much. Now, we can also compare them to electric transducers. These are then again often point sensors. Per sensor, they're often a bit more expensive. They can often monitor continuously, but these electrical components, they can corrode, especially with temperature differences in a saline environment. It is tricky, and you often need to change the battery, for example, and they give very sparse measurements. Now, why this research, I think, has still a lot of potential that we haven't really used to its full extent, is because with recent interrogators, we're also able to probe much larger lengths than we were able to before. For instance, chirp compression gives a lot of more cable length that we can use, or bidirectional Raman scattering. And that also allows us to think about different uses of DAS than just well monitoring and other more conventional applications for DAS. For example, what we would like to do is use DAS at container terminals, because you can imagine once we have a very large container ship, they can stay there for days on end when they are loading or unloading. And this prevents a surveying vessel to measure the nautical depth there. And exactly at these economical, very important locations, you want to have a lot of data, but you often can't because the ski walls are occupied. And there, DAS can also play a very interesting role when we, for instance, would install multiple fibers, as I've shown before. We could say something about the nautical depth at example 90 meters or 20 meters. Do we lose our signal at 20 meters or 90 meters? And then we can, of course, connect our interrogator to the internet, and we can give back live data to the port authorities or other water body authorities, and give an indication about the nautical depth, even when a ship is docked there. Furthermore, I also 2 days ago came back from an experiment where we measured the export cable from a windmill park. And these are cables that are 62, 72 kilometers long. And there we want to apply the same principle as I've shown before to see if we can say something about the cable burial depth. Because remember, once our cable was even touching the sediments, we start to lose a lot of signal. Now, in these cables, as you can see on the red square here, there often is a fiber already installed. And the difficult task is usually to get access to that fiber. And we've been very lucky with a company that granted us access to these cables. And then we want to see, can we do the same, can we apply the same principles to these cables to say something about the burial depth? One problem we have in the Netherlands is, once we consider the location here, there's a lot of sand moving around, which sometimes causes these cables to be exposed or to be completely in the water. And then an anchor can drag over it and can damage these cables. And then the whole windmill park has to be shut down. So that's why I believe that groups like these, we can have a lot of value in, for instance, energy transition, in civil engineering, by applying those into these more niche fields for so far. And with that, I'd like to conclude this presentation and would like to know if anyone has any questions. Yeah, the first hand I saw was from Chris.
Hi there, Menno. That's great presentation. Really nice work. Thank you very much. I have a couple of questions. One was about the measurements using the vessel that were passing and causing the deformation in your hyperbola in the sort of Lloyd's mirror effect. Did you take into account the beam pattern of the fiber itself?
That's a very good point. We had a look at it as well. Of course, we have directional sensitivity. However, this also seems to change per vessel, whereas our directional sensitivity does not change that much per vessel, of course, because it's the same path in essence. They can diverge just a little because the channel is almost half a kilometer wide, but it seemed that it was not really related to the directional sensitivity, because if I go back just a little, where were we? Here we are. The change in frequency here, let's say we go from 100 hertz in just a few meters to maybe 250, is also so large, I would say, or would argue that if we take the whole time over the ship's path, so it passes the whole setup, it also has a somewhat equal distribution for our direction, because we measured it at all locations. And the change, I think, is just too much. Furthermore, I haven't really processed the windmill export cables yet, but as you can imagine, this is at a larger depth. And here we see similar patterns, but with much lower frequencies. And there the same thing holds. We can still integrate over the whole path length and thus would have all directions. But it's a very interesting question you have, because also if you just take certain sections of the path, the picture changes completely.
So I think the closer the ships get to the fiber, the more they're above it, the more variation you'll see due to the beam pattern, because there's always a broadside null from the fiber. The other question I had was about, I think you just skipped over the slides, just a couple down, when you were looking at the waves coming from offshore, the sort of teleseismic waves, I think, the pressure waves. You said that at the frequency, the 0.02 hertz you were using, there, you wouldn't expect any temperature change. Why wouldn't you expect a temperature change?
Because our fibers are in water, and in 50 seconds time, there probably shouldn't be any temperature change. We also have these measuring stations.
Okay, right. I agree that over 50 seconds time, but if you plot them long enough, you should see temperature change from the tide.
Yeah, I agree. Yeah.
But these signals are quite short in time. I get it. Yeah. Okay, thank you. That was a really interesting talk.
Thank you. Yeah, we also looked at the temperature change, but then there's a duration that is equal to the tidal length, which is 12.5 hours. We were fortunate enough that there's a traffic station right around the corner, 200 meters away. And there they also measure the water temperature, the winds and all. But it was very difficult to correlate any of these natural features to what we observed. Hence that we guess it might be seafloor compliance, though it's not very well based, so to say. It's just our best guess at this moment.
Right. It's hard with a small distance. Yeah.
Yeah.
But good work.
I'm also curious about temperature. And wondering, it sounds like you were saying that you do see tidal temperature signals, and how much that varies with burial depth.
So this is a hard one to answer, and the reason for that is it depends on exactly when you are measuring. So once the river temperature is the same as the ocean temperature, you won't observe any temperature change. Then we also have our daily fluctuations from night to day, which is 12 hours instead of 12 and a half. And once we start to integrate over these ultra low frequencies, everything becomes, I wouldn't say spread out, but to go really to frequencies that low, it's always challenging to separate these two. We were able to observe very small changes in strain rate, but actually over the entire fiber. Hence that it still might be something else, such as seafloor compliance. So it's very difficult to really pinpoint which effect is causing what. Is it a daily temperature change due to sun, or is it something like tidal change? We would then have to measure in summer and during fall, winter, all seasons when the difference in river temperature and sea temperature is the largest. But it's still ongoing, but it's very different to separate all of these effects.
Other people are raising their questions, raising their hands. I might ask you other questions related to lower frequency later, but let's see. Megan.
Yeah, thanks, Menno, for the presentation. I had one question / comment and another question. So you said the vortex shedding that you saw was maybe an indicator of depth, but because of the change in frequency. But I was wondering if it was actually a change in the velocity of the flow, because as you have higher velocity, the frequency of the strumming on the cable would change. So I was wondering if you had thought about that.
Yeah, so that's what we plotted here. In green is the tidal flow, which is the velocity. And up is in orange is here the tidal height. And then what we notice is that green doesn't align with our frequency oscillation, whereas orange does. So we actually thought it would be the tidal flow that would cause this oscillation, because I agree, once the flow increases, you would expect a different response, so to say. But it seemed to be that maybe the pole exposure was the more dominant effect rather than the flow velocity in our case.
Yeah,
and
interesting.
Also, when we look over here, the frequency matches the tides perfectly, the tidal height, but not the tidal flow, because then it needs to have half the period, and we could not see anything that was, let's say, half the period of this. Or not, at least what we observed. But yeah, it's an interesting question. I also don't know why exactly that is. And even if we look at very small features here, what I like is even these very small, and we talk about maybe 10 centimeters here, we were still able to capture.
Yeah, that's interesting and strange at the same time.
Yes.
And my other question was, I think in our group, we've been really thinking about coupling of the fiber with the seafloor, and we've been mostly focused on measuring waves. And like in your case, you're saying that when the fiber is exposed in the water, you're actually getting the better signal. Did you expect that going in, or what were your thoughts going into the experiment?
Well, from the laboratory setup, I expected to have more signal. That does not necessarily mean better signal. But what the port authorities are most concerned about is where is water, where is mud, to say it sort of briefly. So in my case, the muting of the signal is a very prominent feature. Whereas if we take, for instance, P wave velocity difference between water and mud, since mud is about 80–90% water, the velocities are about the same. So that's why I really go for this muting effect. This is in line what we expected from the laboratory setup, I would say.
Okay, thank you.
Thank you.
I think Yellen, okay, your question was answered. Okay. Wenbo.
Thanks for the great talk, Menno. I have a question about the DTS, the temperature sensing. So dust companies, they also use the DTS to measure the sediment barrier depth. And so in your opinion, what's the advantage and disadvantage of these two methods? Or first is for the DTS, is it very sensitive to the sediment barrier depth?
Oh, that's a good question. I only have very preliminary results on that I haven't really shared yet. But it's true, like these companies, for instance, where I also measured this export cable from, they have these DTS measurements, usually Brunel, not Raman, which was also new for me. And when we lay or compare our results, we see many striking similarities, but also sometimes not. And what I think is what was mainly the benefit of DAS is you can see phase information. And what it means is that, for example, if I see flow, I know it's really in water. Whereas with a temperature, you cannot really separate the difference between, hey, maybe my cable is not functioning that well, hence that it gets a little bit warmer, or it's not properly covered. So the phase information really allows you to tell you what is going on there. Is the burial depth sufficient or insufficient? Is that why we get certain resonances? Whereas, with these temperature sensing, you only know, okay, I have a certain temperature, but I cannot say, is the cable partially damaged? Is it maybe, is the corner a bit too sharp and hence it's heating? Or is there not enough sediments? So that's why I think these two methods complement each other quite well. And that we should use more DAS on windmill export cables.
Okay, thanks for the great answer.
Thank you for the question. Anyone else?
I guess I'll ask my question, which is for the cable. So you were tensioning between the two posts, and I'm wondering if you ran into any issues with basically overscaling, where you're seeing really abrupt and non-realistic shifts in strain related to like large movements of the cable.
No, I haven't really encountered any of that sort. Of course, sometimes you have one channel that behaves a bit peculiar, so to say, but it was never a whole line. So, if I would look at this, for example, this was, I think, 10 minutes over which I integrated. I don't see anything particularly out of the ordinary. What I did notice is that the lines sometimes behaved a bit different. For example, now line 5 is more prominent than line 4. sometimes that would change, but I can imagine it also depends on the exact vessel orientation with respect to the lines, because one is a little bit deeper, so maybe you get some other constructive and destructive interference paths. I did notice that with other interrogators, though. That was interesting. Yeah, Wenbo?
Yeah, sorry for another question. I think we still have time. Yeah. And another question is about the compliance signal, the very low frequency signal. Did you look at the amplitude of the string? Because here we also look at this very low frequency signal. We did see some like 24 hours period. But when we check out the amplitude, it looks like the amplitude is unreasonably large if we compare it with the compliance theoretical prediction.
Yeah, I did look at the amplitudes also when I looked at a separate channel. I could see it somehow aligned a little with the tidal periods. So I would have a bit more ultra low frequency content during a tidal high and a bit less during a tidal low. What it was difficult to be really saying like, okay, yeah, this is a very clear tidal effect. I think there is more at play there. Because for some tidal cyclists, it did seem to align, and for some it did not. In terms of amplitude, it's hard because we are so low in frequency content that our interrogators also began to struggle to record these ultra low frequencies. If you look at the response function of an interrogator, you see it becomes very, very challenging to record these ultra low frequencies. Ideally, I think we should stack more and more channels, but this was not really feasible in our case because we have a very small setup, a more small field scale setup. So this is something I was thinking about to do with the setup with the windmill export cable.
Okay, great. Yeah, that's very confusing. It's, as you said, DAS, I think it's not designed for measuring such low frequency, but we did see some very, very ultra low frequency signal. Yeah, very confusing signals.
Yeah, I agree. And the question that I got before was whether it's just a machine noise or anything like that. But then I pointed out like, hey, I only have these signals when my fiber is in water, which is not what one would expect if it's just a machine noise, because then it should be, prevalent throughout the entire fiber. It shouldn't be just in the fiber that is suspended in water. So that is why I also think it's a physical phenomenon much rather than a interrogator related phenomenon. Yeah, Megan?
Thanks. Yeah, I had a question about the low frequency as well. Do you have any plots of the PSD from like one channel with where it's frequency and power? We were just seeing some like asymptotic looking ramp at the lowest frequencies, and we're trying to figure that out. So I was wondering if you guys see the same thing.
Yeah, so this is also what I told Wembo before. Like we did create these plots, but they were not very informative. Like I said, they give indications that they might be related to a tidal effect, but for some tidal cycli it did align, and for some it did not. So I can imagine it's also somehow related to the weather far offshore, that it also creates some infragravity waves. And then you have the same thing like with the temperature, what exactly is causing what? So these ultra low frequencies, is it something related to a temperature effect? Well, here I expect not, because when the cable's pressed against the mud, I hardly get any signal, which still is the same temperature as the cable suspended in water. But looking at these individual channels, it was very challenging. If you like, I can send the results to you. And then you see there are times that these low signals are more prominent than others moments, and this is for hours, sometimes 6, sometimes 4. And then it has small amplitudes for a few hours, but it was very difficult to pinpoint exactly what is at play there.
Yeah, I think we're just interested from the, I guess not necessarily interpretation of the signal, just patterns that are seen. And which interrogator did you have? And you probably said it, but I don't remember.
I used initially a Silixa V2 in the lab, then a Fibres A1 for the small VSP setup. And what you're looking here now is from an Optodust from ASN.
Okay.
And also notice the difference in interrogators when capturing these very low frequencies. But I must also say, when we had the interrogator, which we acquired recently, we were able to capture or measure for much longer times, because before we couldn't store it properly. And you don't want to leave an interrogator unattended in the port of Rotterdam. It will be gone.
Okay. Yeah, we can reach out to you, but I think that would be interesting to see some of the like PSDs that you have for the low frequency content for us, if you don't mind sharing.
Of course not. Everything what I presented, I will publish or have published. So feel free to reach out and I can share all the data in essence.
Okay, thank you so much.
Thank you. Anybody else?
Awesome. This was a really wonderful talk. Thank you again for giving this seminar and answering all these questions. I think these seminars are always a great opportunity to share insights and raise mutual questions.
Thank you very much for having me.
Yeah, awesome. Thanks all. And please do get in touch if you'd like to give a seminar in the future, or if you have any thoughts. And thanks all for joining.
All right. Thank you. Bye-bye.
Thanks. Bye.
Thanks. Bye.